So folks, in this video we're going to look at matrices as linear transformations. If you can't remember what a linear transformation is, I recommend that you go back and review the superposition notes that we took, which you can access here. So those were pre-work that we've done. So this is a surprising fact, folks. Every linear transformation that you've studied in this class can be thought of as a matrix. And every matrix that you've studied in this class can be thought of as a linear transformation. So there is a correspondence between matrices and our linear transformations. So maybe you've recognized this fact previously, maybe you haven't. That's okay, we're going to discover it here. But it's actually been staring us in the face all along. So here's a useful fact. Every m by n matrix is itself a linear transformation. That's what I was just saying here. And one way we can think about that is if the entries of the matrix are real valued, then we can think of this transformation T as mapping from, careful here, Rn to Rm. Okay? That is, we could define a transformation T which is going to take vectors that live in n space to vectors that live in m space by doing this. Okay? So here, let's say x is a vector in Rn and y is a vector in Rm. So what we're saying here is that the way this transformation would work is we're going to take some matrix A and we're going to multiply it on the left by the vector x, a vector x living in Rn, and that's going to return a vector y living in Rm. One thing that initially causes students some trouble when we think about this is why do I say an m by n matrix maps from Rn to Rm? But here's how I want you to think about it. If we've got a vector x living in Rn, it looks like some n by 1 column vector. That is, it's got some x1, x2, all the way down to xn. And I'm going to multiply it by something that takes me to Rm, which would be an m by 1 column matrix, or column vector. So that would look like y1, y2, ... down to ym. Noticing that these are not the same number. This has n rows, this has m rows. The question is what do I need to multiply this vector that comes from my domain space, my domain vector space, so that it lands somewhere in my range vector space? And the answer is we need to multiply it by an m by n column matrix. Excuse me, an m by n matrix. So it's got m rows and n columns. So hopefully now we see why an m by n matrix can be thought of as at least a transformation that takes me from one vector space to another vector space. So again here, folks, I'm specifically talking about the real vector spaces of various dimensions here, and not the more abstract vector spaces such as our function spaces, although a number of these ideas that we're exploring can apply to those more abstract vector spaces as well. So there's one thing I think we ought to at least mention is that these are actually linear transformations. And so here, folks, I want to highlight that word linear. What makes this a linear transformation? Again, you can go back and review the definition of it in your superposition notes. But let's go ahead and explore that here. If I were to let A and B be in R, and let's pick any two vectors in Rn, so let's call it x1, that's a vector in Rn, an n by 1 column vector, and x2, we've got these two vectors in Rn, then we could talk about doing the transformation to a linear combination of these two vectors. And that's what I'm denoting here. So what does it mean to be a linear transformation? It means that it preserves linear combinations. So we know that this would be the matrix A, which is our matrix, this m by n matrix, and we're going to be matrix multiplying it by this linear combination right here. But we have our properties of matrices that we've verified, and they still hold even when we're using scalars and n by 1 column vectors. That all holds. And so we could show, first of all, that that would be a times the constant a, not a vector, the constant a times vector x1 plus a times the constant b times the vector x2. But I can then pass that scalar through, and so we end up with a x1, a little a matrix A x1 plus little b matrix A x2. And then what have we just shown? Well, this right here is what it means to do the transformation just to the vector x1. And this right here, the ax2, is what it means to do the transformation to, scoot over there, oops, too far, to the vector x2. And so we've just shown that t is linear. It is in fact a linear transformation, not just a transformation. Okay, folks, this got real abstract real fast. Let's jump into a concrete example next. So folks, the question is, as we go forward, how do we want to think about matrices? And the new perspective is to think of matrices as linear transformations. So let's notice something about this matrix. It has 2 rows and has 3 columns, so its dimension is a 2 by 3 matrix. We've done this before. What's new is we're going to think about this matrix as being a linear transformation, and it's going to map us from one space to another space. The question is, what are those dimensions on those spaces going to be? Let's answer that question. What are those dimensions on those spaces going to be? Well, the way we think about setting up this matrix multiplication is that I want to take and matrix multiply this matrix on the left of some column vector. So this matrix, we just said, has the dimensions 2 by 3, and I want to multiply it by something by 1 column vector. The question is what do those dimensions need to be? Well, for the multiplication to be well defined, that has to be a 3 by 1 column vector. So the entries of that might look like x1, x2, x3. So this matrix, this 2 by 3 matrix, is going to take column vectors from R3, and what's it going to do with them? It's going to map them into Rn. But what's our Rm going to be in this case? Well, this is going to map us to a 2 by 1 column vector. So just by the way we've defined our matrix multiplication, then we're going to end up with our y1, y2, and that's where this is going to be a, that we can think of this matrix A as taking us from R3 to R2. Okay? So that's how we're thinking about these transformations. We've said that they're linear. They're going to be a way, I think of this as encoding how we're going to morph all of 3 space down into 2 space. We could go the other direction too. We could sort of insert 2 space into 3 space by doing some sort of folding and expanding and contracting, and ask the question, what's that going to look like? So these are our transformations, simply our n by n matrices. So the question is, what's this all going to look like? And here I'd like to actually draw a little sketch, and we'll trace out some vectors here. So let's see here. For my R3, this is our R3 space. Now, folks, I don't actually have to draw these coordinate axes, but we're just used to drawing them when we draw R3. But let me go ahead and label some tick marks on here because I want to reference those. We'll go out 3 tick marks, 1 tick mark here, and then we'll go up 2 tick marks here for what I want to show you. And we're going to be mapping vectors in this space into R2. So here's our R2, and I need to make a few tick marks on this, so we could go out 1, 2, 3, 4, 5, 6, 7 will be enough for this, and up 1, 2, we'll go up to 3, down 1, 2, 3, and let's go backwards 1, 2, 3. So this is our R2, and I'm only putting these coordinates on here to help me be able to represent where these vectors lie as we think of them as mapping from one space to another. And let's go ahead and pick some of these vectors. So let's take this vector right here, which is our I hat vector, but we can just think of it as any old vector. And we would represent that in R3 as the vector 1, 0, 0, using the standard coordinate basis. And so we can ask the question, if we were to take t of our vector there, so that is, we're going to do this linear transformation to this vector, which is going to take us from the R3 vector space to the R2 vector space. How do we actually do that computation? Well, we're doing it by multiplying it on the left to this matrix. And if I do this multiplication, you can do it with me. We'll do this row by this column, which gives me the entry 1. And then if we do this row by this column, it gives me the entry minus 1. And you should notice something, that if I take a matrix that's written as a matrix in terms of the ordinary basis vectors, and then I multiply it by those basis vectors, you'll notice that I end up with my first column being the result of what happened to that first basis vector. So let's go plot this vector now, 1, -1. So that would be this vector right here. So you could imagine this function, this linear transformation t, as taking this vector right here and morphing it into 2 space based on this 2 by 3 matrix. And we could keep going. We could take t of our other basis vectors. Let's do that. Where I actually didn't do the computation for this last vector, I just knew that it was going to give me the third column of my original transformation matrix. So let's go plot that. That's the vector now 2, 1, which would be this vector right here. And so you can actually see where these vectors in 3 space got moved to 2-dimensional vectors in 2 space based on this transformation. For fun, let's do one more vector. So we're going to take and look at what happens with this vector 3, 1, 2 here. So let's take a look at that. If I were to go out 3 on the x-axis, out 1 on the y-axis, and up 2 on the z-axis, that would give me this vector right here. This is the vector 3, 1, 2. And if we were to look at where that gets mapped, that's a little bit more interesting because we can't really predict it ahead of time. And so let's take it, 3, 1, 2. And I'll let you verify that if we do the matrix multiplication for this, that we end up with the vector 7, 2. Let's plot that. The vector 7, 2 lands somewhere about over here. There's the vector 7, 2. So folks, this is just a way to try to visualize what these transformations are doing. This is a little bit misleading in that I'm specifically picking R3 as my domain space and R2 as my range space under this vector transformation, this transformation from one space to another. And both of these can easily be visualized, or relatively easily be visualized. I guess, drawing that purple vector was a little rough there. But we can imagine this transformation. Really, we would need to see what this transformation does to all of this space, and those diagrams can get very messy. So that's how we can think of every single matrix as a linear transformation. That finishes up this video. In the next video, we're going to look at something a little bit more surprising, that every linear transformation can be represented by an n by n matrix. So I'll see you there.